picking up where we left off from yesterday, what we finished with was thinking about rise over run in the specific context where you have a curve like this and its gradient is changing all the time, right? So gradient, like we usually with straight lines, corner geometry and so on, we say, oh, gradient, we'll just call it m, right? Because it's just a number, it's just a constant, it's not changing, it's not variable, right? But here, m's not going to cut it. M's not going to cut it because in fact the gradient is not a number, it's not a constant, it is a function itself. The gradient is changing wherever you look, right? So therefore, we replace this idea of the gradient as a constant with the gradient as a function. In fact, we call it the gradient function, right? And rather than say rise over run, which is just kind of a nice mnemonic way of remembering what gradient is, we said rise is really the change, d, delta, the change in y, and run is really the change in x. And that's where we get this dy over dx notation from, okay? Now, one word I didn't introduce yesterday is that we call this thing not just the gradient, right? But now that it's a function, it's its own thing, we call it the derivative. And derivative, you know, it just means it comes from something else, right? Namely, it comes from the actual function, right? We learnt this way of taking this rise over run and putting on all these different points and comparing it with limits to what was happening at a particular point on there. Okay, so this is the introduction, the actual thing that we said was first principles, right? We said f dash, which is just yet another way of indicating the notation, right, is equal to the limit as h approaches 0 of, now what was our numerator? What was it? F of
x plus h.
f of x plus h,
Minus
and then we
f.
take away f of x. Now, just remember, why do we do that? It's because f of x plus h is here, and f of x is here, and we just want the difference. That's all it is, that's the rise. And of course, there's the run. Do you remember, when I said to you we're introducing this topic, the worst thing that you can do is just get to work memorizing stuff and not know where it comes from. I remember sitting next to you when I was in year 11, sitting next to people who were just like, look, it's just memorize it, okay? Doesn't matter what any of it means, okay? That's the quickest way to get on the path of not actually understanding what's happening. This is rise, right? This is run. One last thing. What difference does that make? If it weren't there, that limit as h approaches 0, if it weren't there, it's not meaningless, but what would it be? It'd be something else. Yeah.
Gradient.
It'd be the gradient of
Line.
not the tangent. The tangent's what we want, right? But if you've got 2 points that are actually apart, it'll be the secant, won't it? Right? It's not meaningless. That's how we started. It's just not what we want. This is the gradient of the tangent, the derivative. Without that, and many people are like, oh, I have to write this over and over again. Without that, it's the gradient of the secant. We're not after that. Okay, so now that's where we stopped, right? Now we want to apply it to a particular situation, okay? So here's a function, right? Now, the one we'll start with, the easiest one to start with, is just the parabola, x squared, okay? If you see f of x, right, then you can use this f dash x notation, okay? If, on the other hand, all you see is this, there is no function called f, right? So none of this really makes sense. F dash, what is any of that in here? You would have to use this notation up here, right? If you've got y's, you'd use dy and dx. If you've got f's, you'd use f and f dash, okay? Now, I'm just going to come back because for this example, we're just starting off. I do actually want to go with f's because it'll make this a bit easier. So this is f of x equals x squared, okay? Let's proceed through this, right? If f of x is that, then f dash x is going to equal to. Now, it begins with just a substitution. If we know what f is, I should know what all those pieces are in there. Okay, so we begin with the limit because I'm interested in the tangent and not the secant. If f of x is x squared, then f of x plus h is x plus h all squared. You agree with that? And there's f of x just as we defined it. We're dividing through by h. Okay? Now, what we're about to do is what we call evaluating the derivative from first principles. Like, this is our starting point. Okay? What we're trying to do is manipulate this in such a way such that I can actually put h equals 0 in there and see what happens. I can't do that right now because h is on the denominator. You divide by 0, it explodes. Okay, so I want to reshape this into something that gets rid of h being just by itself on the denominator. Okay, so let's give this a go. Obviously, you look at the numerator. That's the only thing you can do anything with here. The denominator is just simplified. So I write my limit because I want the tangent, not the secant. You're going to get really sick of me saying that, but I want you to get in your head. It's really important to keep on saying it. On the numerator, perfect square. When you expand it, you get x squared plus 2hx plus h squared, and then there's that minus x squared tacking along the end. Okay, and then of course everything is divided by h, right? Just because you're not doing any work with them, don't forget to write this or the denominator. They're still there and they're still critically important. Having expanded, you can see I can do something with this now, can't I? Got an x squared on the front, minus x squared on the back, and they're going to cancel each other out. Okay. Now the reason why this is good is because now I have a common factor of h on the numerator, right? Common factor of h, let me take it out, let me factorize it. Limit as h approaches 0, because I want the tangent, not the secant, of what's on the numerator? What's on the numerator?
Oh, sorry.
H outside of
2x
2x plus h. Good, there's still an h hanging around there. That's all divided through by h. Okay? Fantastic. Now I can cancel. Denominator's gone. Yep.
Isn't that like the equivalent of dividing like by
Cancelling out.
Times it by 0 over 0, which is undefined.
Yes, this is exactly right. I'm glad you raised that point. Why can I get rid of this? Okay, let me pull back to, do you remember when you look at this? This. Okay, now what does this thing look like? Okay, sorry, yeah. Thank you. Okay. Now, I was on autopilot for a second. What does this thing look like? Even though it's got an x squared on the top, because of what you get on the bottom, you're actually going to get a straight line, aren't you? Okay, when you factorize, x approaches negative 1, x minus 1, x plus 1. You okay with that? You okay with that? So what does this thing actually look like? It looks like this straight line with one difference. Namely, there's a hole there. There's just a hole. Right? So, x minus 1, what does that look like? Down here. And x equals negative 1, maybe somewhere over here, I guess. There's my little hole there. Okay? So, our problem is, I can't simply input x equals negative 1 because then, as you notice, I'm multiplying by 0 and dividing by 0, and it loses meaning. Okay? However, what I'm just come back to when we define this idea of a limit, right? What I'm trying to think about is, what am I getting towards, right? And I am actually getting towards something real, even though I can't be there itself any more than I can calculate the gradient of, a point to itself. That's what this is really doing, rise over run as the 2 points get close together, right? I can't actually calculate that, but I can still see what it's approaching. And if it's approaching the same thing from both angles, then that's fine. That's great. I can take that as a meaningful result. Okay? So, a very good point to mention, because it's like, yeah, why can I do that? And the answer is because h can't be actually equal to 0, so I can take it out of the equation. Okay. Expression, I should say. Now that I've done this is the last time I'm going to write the limit as h approaches 0, because I want, say it with me, the tangent, not the secant, right? Just like a hammer. Anyway, okay. So now that I'm there, I've gotten rid of h on the denominator, right? By the way, h can be on the denominator, just not by itself. Because when it's by itself, the denominator becomes 0, as you'll see shortly. Now I actually can say, well, let's just see what happens when h is 0. And the answer is, it's 2x plus 0. Don't miss the plus 0, it's not trivial, okay? Just like multiplying by 1 sometimes is not trivial, adding 0 is not trivial, because I see it comes from here. And that, of course, is just 2x. Okay, what's this mean?